Welcome everyone and thank you for joining us today. Our speaker who will be presenting today is Swarnamalya Mohan, a senior AI and machine learning developer at FedEx, where she specializes in building and deploying intelligent systems for enterprise logistics and supply chain. She has deep expertise in model training, machine learning workflows, and AI at scale. Today she'll be walking us through how to go beyond prompt engineering and actually adapt your own language model for a specialized task, covering everything from dataset preparation to fine-tuning techniques like LoRA and QLoRA. Whether you're brand new to machine learning or looking to level up, this session has something for you. Please join me in welcoming Swarnamalaya Mohan.
Thank you so much, and hello everyone. And thank you, TechShare, for the introduction, and thanks for inviting me for the speaker series. And I'm more than excited to talk about this title, which is to train and adapt the own machine learning language model. And I promise you all that you'll walk away with three key takeaways in this session. So firstly, we're going to discuss what are the limitations that exist with the prompt engineering context today. And secondly, we're going to take a look at what is foundation model, what are pre-training techniques, what is fine-tuning techniques, and many more on that. And thirdly, we're going to explore the advanced strategies like the LoRA, the supervised fine-tuning, the reinforcement-based fine-tuning based on the human feedback. And this session is not just going to be conceptual based on slides. So we're also going to connect these to working ideas in the notebook collab sessions. So let's get started. So firstly, let's understand what are the differences that differentiates between the prompting and the model adaptation technique. So starting with what prompting is. So prompting is nothing but the guiding instructions to any of the machine learning model that defines what persona is, what behavior the model has to exhibit, and what are the limitations, constraints, and what the model has to do and what the model shouldn't do. So while we define what prompting is, this is primarily just the changes to the model input context, and we're not changing any of the model parameters with any of the prompting strategies. And we all know that prompting is primarily running during the model inference, and it has nothing to do with any of the model training. So there is no need for any comprehensive model training pipelines involved in prompting. So it's very fast, inexpensive, and it's very straightforward in nature, but the behavior is very inconsistent, meaning you might not expect the same anticipated answers in every phrasings. But when it comes to model adaptation is basically defining the model, what objective it is, and training it on a labeled or an unlabeled data set, and measuring what is the loss and computing its accuracy and many other metrics. So that's a very sophisticated and a comprehensive training pipeline that model training has to undergo. But it is very consistent and reusable in nature. So you do not have to prompt for the model to get the right answers from it. And always any model that's trained will require a complete end-to-end evaluation, because there is always a difference in the training set and the test and validation set. So every model has to be evaluated based on the test and validation set. So these are some things that we're going to take a look in detail in the following slides. So with this, let's take a view on what the model adaptation spectrum looks like. So we see there is the one that starts with prompting with 0 weight updates on the left. And as it goes towards the right, you see the pre-training on the right with a complete weight update. So this graph represents incremental or a linear increase of cost, where prompting starts with a very hassle-free and simpler prompting strategy. But while you see on the right, pre-training involves massive computation costs, massive resources, and many constraints like memory and GPUs and many more. So this is how the spectrum varies from left to right, where prompting follows the instructions based on what instruction the user prompts the model, and following which the second one is RAG, which stands for Retrieval Augmented Generation. And this is something where we are expecting the model to give grounded response rather than letting the LLM hallucinate on its own. We are asking the model to fetch the answers from a grounded knowledge base articles. And that's how RAG improves from a simple model that just hallucinates in case if it's not aware of a particular context. And now comes the model training or model adaptation strategies. The first one starting with the supervised fine tuning, where there is a full weight update because it undergoes a full training of the base model. And it also incurs a cost that's accountable for the training. And next comes the adapting strategies, which is the parameter efficient fine tuning and the low rank adaptation technique. So these are some things that we're going to take a detailed view in the further slides. And this also requires a cost, but which is relatively a very on a lower end. And the third one is the reinforcement based learning on human feedback. And there are optimization techniques like the group relative optimization technique. So this is like a policy optimization technique that applies for ranking the precedence of answers. So this also involves a higher cost because it works on training a reward model. And next comes the pre-training. So pre-training is like creating a base model from a broader data or a diverse data where we are updating all the weights of a model starting from a random uninitialized weights to a fully trained model. And this has a very good capability of as a general model, so it performs very good in generalization. And the cost required is definitely high because when we're talking about pre-training, the weights involved is like billions and trillions. So the parameters are very massive. So this is how on an overall the model adaptation looks like and how we progress right from prompting to involving training models and using adaptive techniques, and what are the costs involved, what are the weight updates, and how each one looks relative to the other. Now, let's get started to explore why prompting is powerful, but it stops being sufficient, right? Now, consider an example where there is a misspelled sentence and we are wanting to have the spelling corrected. Basically, the underlying task is same. We want the spelling to be corrected, but we get started with a very vague prompt where we do not define anything other than just a task in a simple sentence. So we're just asking the model to say, fix the spelling in the sentence. Well, the model does it well. So the language model is powerful, is the expected correct sentence, but it also appends an additional sentence, right? I have fixed the spelling errors. So this may or may not pass a downstream validation constraint based on what our validation constraint is. So if we have like an exact matching algorithm where we just match the correct sentence with the output, this will certainly fail, right? So this is a very vague prompt where we're just describing the task. And next, we are trying to fine tune to make it more precise, where we are asking the correct the spelling, but return only the corrected sentence. And here's how the model will return the output with the corrected sentence. And one thing to note that this prompt might give us the right output with this particular input, but it might not be the same consistent with all the sentences. So it's very inconsistent and it cannot be reusable in all the cases. So this is one precise prompt, but still we are missing to define the role. We are missing to define the constraints or the limitations. So here's where we progress for the role-based, where we are defining what its persona is. So you act as a spelling corrector, right? So this is your role, this is your persona, and fix this text. So in this way, it fixes the text and also gives us what are the errors that it has fixed. So in this case, we notice 3 errors. One is in the first word, second word, and third word. So it highlights what are 3 errors fixed. So this is how prompting varies with how powerful it is and how relevant the prompt context is. So it all depends on how good prompt that we are providing into the model. And we also have different prompting strategies like, zero shot prompting, few shot prompting, where we are giving instances or examples with input output pairs that helps the model to understand what is the expected requirement and what output structure it has to follow. So those are the other techniques that prompt engineering has in overall. So there is like chain of thought as well, where it reasons behind its answer. So those are the other information that we have regarding the prompting. But all of this serves as a very inconsistent behavior because it might not exhibit the same behavior at all phrasings. So this demands us to use training of model or adaptation of a machine learning model. So now let's get started with the model training. So before I jump to what we have about your LLMs or what about Gen AIs, let's talk about a traditional machine learning model starting from the neural nets. So we all know that every machine learning model requires a training cycle or a loop of execution. So any trainable machine learning model follows the exact same execution cycle or a training cycle. So any machine learning model has to be fed with an input, and the model does produce a prediction on that input. And once we have the prediction from the model, we will have to compute the loss. So loss is nothing but the difference between the predicted output and the actual output. And in order to identify the loss, there are loss functions that enables us to identify what is the difference that's encountered between the predicted and the actual function. With this loss value, the model performs back propagation. So until this step, it is called as forward pass. But once it gets the output and identifies the loss, it starts to back propagate. So back propagation is nothing but identifying what amount of error or how much of a parameter has contributed to error. So that value is identified by the back propagation. And once it identifies that, the value is being updated using an optimizer. So the optimizer tries to update the weight values or the model parameters in a direction that goes to minimize the loss. So our entire intent of this model training is to get started with input, compute the loss, and then go in the direction of reducing the loss. So here's how the gradient descent update rule looks like. So the gradient descent update is basically done by the optimizer, where we have the theta value. Theta is nothing but a machine learning parameter value. And the theta is updated by learning rate times the gradient of the loss function. So this is the learning rate, and this is the gradient of the loss function. Basically, learning rate is the factor that controls how much update has to take place with the weights or the model parameters. So if we have the learning rate set very small, then the learning process becomes very slow. But if we set the learning rate too high, then the learning becomes more unstable or it tends to just diverge. So choosing the ideal learning rate is very critical and essential for a very stable and accurate machine learning model. Now, here's again an illustration where I just want to show how the loss goes over time. So initially the epoch zero. So epoch is nothing but considered like a step in a training process. So at step zero, we see the loss is at a value 2.31. And as it progresses with the training cycle, at epoch n, which is the step n, the loss goes with a significant decrease, 2.14. So this is just an illustration how the model training takes place, and it goes with the objective of reducing the loss function. With this, I have an illustration in a notebook where I would like to show how we just yeah how we implement training in a neural network. Okay, so every neural network comprises of interconnected nodes. So assume a node is like a single unit in a neural network where it receives the input and passes the output to its next corresponding node. So it's like an interconnected network of nodes. And every node is put in like three different layers. Firstly, the input layer, intermediate layer, and output layer. So this system of having a composed of multiple nodes with layers is called as multi-layer perceptron. So a multi-layer perceptron is easier to define. So first thing is we define what is the hidden layer architecture, where we are talking about what is the input size and how it transitions to the intermediate or the hidden layer. So the next one is the output layer, where it transitions from the hidden layer to the output layer. So this one, so in this case, the input size is 10. So this can be imagined like where the input size is 10, it transitions to 64. Again, from 64 intermediate layers, it goes back to give output with just two values. So this is how this multi-layer perceptron architecture has been defined in this example. Now, so this is an activation layer. So activation layer is nothing but to understand what are the non-linear relationships that exist between the nodes, right? So the information is just a raw information that's being passed as input. So that has to be interpreted, what meaning, what semantic relationship exists, and all that is done by the activation function. So in this case, it is called as the ReLU activation, where in mathematical terms, it's just put like, maximum of the value comma 0. So in case if it is minus 2 0, the value 0 is considered. In case if it is 3 and 0, the max of 3 and 0 is 3. So this is how the activation function serves in this use case. And yeah, this is how the MLP architecture looks like, with 10 values as input, 64 as intermediate, and the 64 intermediate nodes getting branched out to just two output. Now, looking at the loss function, since I spoke about the loss function in our training cycle loop, where it computes the difference between the input and the output, here's an example where I would like to show how the loss function looks like. So consider our output is nothing but a single unit, either being 0 or 1. So it's basically labeling 0 for cats and 1 for dogs. And we are using cross entropy loss function, so which is very well suited for the classification tasks. And there are two loss functions. So one is the mean squared loss function, error loss function, and the cross entropy. So cross entropy fits very well for our classification tasks, while the mean squared error fits very well for regression tasks, since there are two types of task classifications. Like one is where the label is just strictly 0 1, and regression is something like it predicts the forecast in which range of values it falls under, rather than just a strict 0 or 1, right? So in this case, it is clearly a classification task where we just want to predict a label which is 0 or 1, which is 0 for cats and 1 for dogs. Now, here is the output that the model has given. So this is the logits, or you can say it as raw values that the model has given, with 2 and 5. Now we see here that it has given the more likelihood to dog, right? Because it has predicted the value of dog with a higher probability, or with a higher value, or with a higher weight compared to cat. And we know that given that the label is already dog, the actual output is dog, and the predicted output for dog is highly likely. So in this case, the loss is expected to be less, and the loss value is 0.0486. Now take a second example where the model has given this as a prediction result, with 1.5 as the value for cat and 1.1 for the value of dog. Now you see in this case, the weights or the logits produced for the cat is higher than dog, which is not actually mapping with the actual label, which is dog. So in this case, our loss is expected to be higher. So we see that this is 0.9 compared to the previous loss. So this is how the loss function works when we are doing a training cycle. And our intention is to minimize this loss value in the end. Now this is the same. This is a different example using the MSE, which is the mean squared error. As I mentioned, MSE is for the regression problems. Now for the regression problems, we have, this is the predicted price from the model. This is the actual price. So what is the loss for it? So it's basically computing what could be the probability difference, or between the actual and the predicted and giving us the MSE, which is the mean squared error. So here are the loss functions, and now coming to the optimizers. So optimizers does the update to the weight values. So after we identify the loss, there's a back propagation to identify what value contributes to error. And after identifying that, optimizer actually updates the weight values based on the gradient. Now there are two optimizers again. One is the stochastic gradient optimizer, and the second one is Adam optimizer. And both are basically a good optimizers and can be used more interchangeably. And in this example, we are going to use the SGD, and we are also going to see what difference looks like between both the optimizers. Now coming to the training loop. So this is a very simple training example that I've considered for illustration. So we want to know what is the sum of two numbers, and we want the model to predict that output. So we're just training the model to compute the sum of two numbers. Okay. Now to tell the model how it has to perform, we will have to give a list of input. So we will have to say that if the input is 0 and 0, the output is 0. If the input is 0, 1, the output is 1, which is basically we are providing the list of two digits and its corresponding output. So the model learns from the input, identifies what relationship exists between the input, and tries to map it to a rule and produces the output. This is our underlying logic in any training models, defining the objective, and then the model performs the understanding and prediction parts. Now, we are generating the data set by passing it from a range. So the range is 5 in this case to print it. So it's just printing the 5 numbers. Now, we are defining the multi-layer perceptron architecture for this training example. And we start with two values, right? Two input values. And we go with one output, which is the sum of the two input values. And this is the intermediate architecture, which is 128. So we see, 128 cross 2 matrix in the intermediate nodes. And finally, it transforms to 128 cross 1, where the output is just one value. Now, here we're defining the number set data set and data range is 10. So we are defining the 10 input examples. And the data loader is like a helper function for us to load. And we are defining the batch size as 10, which means each batch will have 10 input examples, and 10 batches will have 10 cross 10, which is 100. So this data set is basically a 100 input data set, and we are shuffling it just to avoid the bias. So we just shuffle any data provided. Any machine learning model shuffling is very important because we are just trying to remove or eliminate any biases that exists. And then we are calling the architecture, which is the sum MLP model. So this is the sum MLP architecture that we have defined, and we are assigning that to the model. And here's the loss function, which is the MSE loss function, because this is not a classification task and this is a regression problem. So we are going to use the mean squared error. And here's the optimizer, which is the Adam optimizer with the learning rate set as 0.01, which is quite fair and ideal for this use case. And now starts the training loop. So epochs. So epochs is nothing but the number of steps each training cycle has to follow. So let's say in this case we have defined as 20, which means the 100 data input data will undergo 20 times training in each epoch. So with each epoch, what it follows is, first thing, it clears all the gradients. So gradients is nothing but the loss or the difference that we will have to identify. So first is it zeroes out all the gradients just to clear the previous gradients in case if it exists. And now we are getting the model predictions by invoking the model. And now we identify the loss using the loss function, which in this case is the MSE. And once we identify the loss function, we will have to do the backward propagation. And that's where we invoke the method called as loss.backward. And once we have the backward propagation identified, how much of value has to be updated to minimize the error, we have the value and the optimizer does the gradient update. So once the optimizer updates the weight values in order to minimize in the direction of minimizing or reducing the loss value, we are computing what is the loss. So this loss is just like a cumulative sum of what is the loss in each of the epoch. So because it's 20 epochs, so it has to identify the loss in each of the epoch and gives us a cumulative value for each of the epoch. Now, this is how the training cycle looks like. It starts with a higher loss, and we see that gradually it goes on decreasing because our objective is to have like the loss reduced in such a way that the weights are getting updated towards the correct output. So this is how the training cycle looks like. And for this illustration, I've just given 20 epochs, but in real time, when we work on having the training models, so we primarily deal with, 200 to 500 epochs, or it depends on the trainable batch size that we are trying to use. And also the training cycle will anyway take from uh, 24 to 48 hours, depending on the input cycle that we have. So that's how the range of training goes. And once we have the training performed, we do the prediction on the trained data. So this is the test set. So this is the test tensors we have, and we are invoking the model to predict the what are the prediction, and we see that the model has predicted right. So this is how we start with a simple architecture model, which knows nothing at that moment. It's basically we're just defining what model layers are with no information at that point, and we are training it with an input data set. And the training involves computing loss and going in the direction of reducing loss. In that way, we are matching what the input is and how the model should learn to predict the output. We are training the model with the smaller baby steps, with starting from what the input is and how the model output should be expected. And then once we have the model completely ready, trained, and we are using the evaluation strategy. So this is the core training execution loop that any machine learning model follows. Now, I have another illustration because this one, the previous one was like kind of, regression task. Now I just want to show you in overall how the classification task looks like. I'm not going to give you like a detailed explanation because this is on similar lines, just that we are using image in this case rather than numbers. We are treating an image. So for this, I am taking a handwritten digit data set. So I'm taking like a handwritten digit data set, and the objective of this model is to determine what digit it belongs to. So this is a handwritten digit number 5. So the model has to output 5. So we are training the model to identify the digits from 1 to 10. So in this case, since it is an image, how do we handle images as input, right? So model just understands in terms of tensors. So you pass numbers, you pass text, you pass images, everything, all that it understands is just in terms of tensors. So first thing is we transform it to tensors and we normalize the values. So this is basically to flatten the values, right? Because you're getting an image of 28 cross 28. So how do we flatten them into just tensor values? So this is an extra operation that we perform whenever we encounter images. And in this case, we are having two folders in the data set. And this data set is basically invoked from the existing library. And we are just having train and test data set. And we are also creating a validation data set out of the train data set. And this is how the input looks like. And we are following the same structure as we did previously. So identifying the first making the zeroing the gradients, identifying the predictions, identifying the loss, doing the backward propagation, and applying the optimizer to update the gradients. And now we do the evaluation step. So since it's an image, the evaluation, everything follows on how images are being evaluated. So this is how the training looks like, where it gets started with a higher loss, and this is the accuracy metrics that's computed parallelly, and this is the loss. We see that it goes towards reducing the loss. And now in this case, we are comparing it with two optimizer. One is stochastic gradient descent, and the other one is Adam optimizer. And here's the final evaluation, and we see that how they overlap each other, both the stochastic, the one in the blue is the stochastic gradient descent, and the one in the orange is Adam optimizer. This is how they overlap each other in terms of the loss values and the validation accuracy with epochs. So final accuracy is 97%, and the best optimizer chosen is the SGD model, which is the stochastic gradient descent. So you go with any task, the underlying principle is just the same, where we define the input data set, define the parameters, configurations, the training loop, and perform the evaluation strategies towards the end. So with this, now let's go back to the slide. Okay, so the one that we previously saw was a neural network. And now let's take a look at what foundation models are. So foundation model is something where the model is basically trained on diverse, broad, large corpus of data. So basically the data is on a very larger scale and it is broad and diverse across. There is no specific data. It is just trained on all that it gets to be dumped to the model. So because of that, the foundation model has a capability to understand, perform many tasks at once. So a foundation model can act as a classification, can also perform summarization, can also do embeddings, can also generate code, can also do the Q&A, can also produce structured output as we expect. So that's how foundation model serves as it. The reason being it is able to be flexible with all the tasks is because it is being pre-trained on a broader spectrum of data, and it has the capability to understand the general patterns. It can understand what grammar is, what syntax is, how task patterns operate. So it can understand the semantic relationships between everything. So that's what defines a foundation model. And it's very reusable for many downstream applications. It's not just specific to one particular task, it is reusable in many downstream applications and tasks. And with this, you can also make it more adaptable, right? Because a foundation model may not perform as much as accurate as a adapted model for a specific use case. So it can be made adaptable by using prompting techniques, by using fine-tuning strategies, using the adapted methodologies. So I would also like to show another interesting one that I very often look into. So this is called as Open Router AI models. And this displays us with all the information that's getting updated every day with respect to a new model that's getting generated, built, or established. So we see that in today, the text model itself is 339 models out there. So we have like 339 models, uh, which is basically just like for text models. And these are the models, and you see the token size of it. It is 6.31 billion tokens, which is very massive to imagine. And every day the list gets updated, and you see the image models is about 37 models. And you can also see the rankings of the models. So the top models, and this allows me to use, access the top models, getting more powerful response. So I don't always use, ChatGPT or Claude. I try to explore the top model rankings and try to see what, yeah. So in this case, there's the leaderboard, how it looks like, the LLM leaderboard, and you see this is the one that's ranked the most popular. So you can also rank it by, you know, let's see, by image, by embeddings, and yeah, everything. So this gives you a great insight on how to access what models are out there in market today. And it gives us a complete view of how many models are existing and how do we access them. So this is one website where I very often look into and use it for my daily use case. So just wanted to add this. And yeah, this is how the foundation models are very powerful and booming in today's world. With this, let's take a look at the LLM. So since you already saw how many of LLMs are at scale in today's world, So, but how do they operate, right? So, how do these LLMs operate? And all these are basically following the same principle, which is next token prediction at scale. So, the LLMs get started with text, and each text is tokenized into individual batches or individual units or individual chunks. You can call it as like a smallest entity in a text. And once we have these tokens, it is converted into embeddings. So, embeddings are nothing but the vector notation of a text. So, it could be like, let's say there is a word called so the word is converted into vector notation. So it is something that it can be mapped to a vector space, and it symbolizes its meaning. So words with similar meaning stays closer in the vector space mapping. So that's how embeddings play a very important role. And once we have these embeddings, these are passed to the transformer architecture. So transformer architecture is nothing but a composition of feed-forward network. The uh, it's like composed of many layers with many architectural components, and this transformer tries to predict what is the next word. So it gives us raw logits or something called as raw scores on what the next word is predicted. And then once we have these raw scores or raw predictions, that is converted into probabilities, the token probability. What is the probability distribution of having this word coming after this in the sequence? So provided this is the previous word, what is the probability of the next word? So it's basically operating in identifying the probability distribution of the next set of words in the vocabulary. And that's how the next token prediction works in LLMs. And this is the training objective equation, right? So the one that you see here is basically trying to identify what is the probability of the upcoming words, provided this is the previous word in the sequence. So this is the training objective, and its equation called as its equation is called as the maximizing the log likelihood. Now consider an example where this is a sentence: the model learns. Now, when you pass this to this LLM, so what is the probability of the next word, or how it predicts the next word? Now, this is the sentence that says model learns. Now, here's the list of vocabulary that it exhibits with its probability values. So it says the model learns patterns, and this is the probability distribution. It says model learns representations with this probability of having representations as the next word. But when you look at the next two word, the probability goes significantly lower. So it gives precedence to the first two words, with patterns having the higher precedence. This is how the next token probability distribution works, and every LLM in today's case is basically operating on this underlying principle. Now, how do we build this? How do we build this next token prediction sequence, right? So we took a look at how it predicts it, but how do we build this model? Well, to build this, it's getting started with a large unlabeled corpus of data, which is like very broad, very diverse in nature. And it is getting started with random weights. Uninitialized random weights is the starting point. So we are just starting gathering data from all sources and unlabeled in nature. And then the data is basically tokenized into batches because the data size is very massive. So we will have to tokenize into batches. And then there's a forward pass where it predicts, and then there's a computation of loss between the predicted value and the actual token. So in this case, the model predicts the next token. So the loss is basically the difference between the predicted token and what the actual token is, right? So that's the loss. Once we have the loss, then there's a back propagation followed, and then there is a update to the model weights using the optimizer. So this is how the model starts with random weights or untrained weights and goes through an entire cycle of pre-training, updates billions of gradient parameters or gradient model weights, and then attains a model that has minimal loss and is capable of doing generalized tasks. So this is how the pre-training starts, and we build a foundation model just starting with random weights. And this model will be capable of understanding the grammar, syntax, knowing the task patterns, and these are very generalized, or it can it's there's no domain specialization that's followed here, so it's very generic in nature. And its computation cost is relatively high because as we took a look at the models, they are ranging from anywhere between billions, like 6.3 billions. So the computation cost, the resource, everything is at a very high rent. And this is how we build the pre-training, perform the pre-training to build a foundation model. Now, let's see what's the difference between pre-training and fine-tuning, right? So we took a look at what pre-training is, but now we're going to introduce a new concept called as fine-tuning. Pre-training, we started with random uninitialized weights, and it had a broad corpus of data. So the data was large, diverse. It involved every aspect of data, and the output is basically a generic model that's capable of doing any capacity or at any capacity with any task. And the compute resource, everything was high in case of pre-training. Now, with fine-tuning, what differs? One is the initialization, which means we are getting started with the pre-trained model. So we're getting started with the pre-trained model rather than like from scratch. And what are the examples? We are going to give the task specific example. So basically fine tuning is required when we want to adapt this pre-training model to a very specific task. I do not want a model that is generic in capability. I want it to perform this specific task for me and with higher accuracy, which is not expected in a foundation model. So that's when I adopt the fine tuning technique, use the pre-trained model or use the base foundation model, use that and provide with my own task examples and try to get the model specialized to my task. So basically I'm doing the model adaptation to my domain, and the computation cost is definitely lower because I'm not using a large diverse set of example that's available out there. So I'm just using the examples that's fine-tuned to my use case. And here's how you can imagine, like the general base model has general knowledge from all sources and requires so much of data, so much of resources. But while you use that to adapt it to a fine-tuned task, you use a smaller set of data which is relevant to your task and to the adaptation process. So this is how you're following the same training loop, but starting from a different point where you're passing it from not from a scratch, but you're starting it from the already pre-trained model. Now, we took a look at what pre-training is, what fine-tuning is. Now, let's see how we are doing the fine-tuning through different strategies. One is supervised fine-tuning. So supervised fine-tuning is nothing but learning, teaching the model to learn using a specific task-based examples, which is labeled in nature. Now, consider an example here. You want the model to act like a spelling corrector, where it has to correct the misspelled sentences, and you pass the instruction, and this is the input with the misspelled sentence, and the response is the corrected sentence. So you're basically formulating a training or labeled data set, and you're passing that to the model to learn. So this is the simple principle behind the supervised fine tuning, where we are passing the labeled data set and asking the model to learn based on the instances. And in whenever it is trained, we pass in another sentence. It should be capable of correcting the spelling. So now we are trying to get a model that's basically specializing in correcting the spelling. Now, how do we do that? So we pass the input output response pairs with the instructions. So that's our input data set in this scenario to train. Once we have this, it does the same process by tokenizing the input output pair response and then follows the same language modeling where it computes the loss based on the next word prediction. So it predicts the next word, identifies what is the actual word, computes the loss, and then it does the back propagation, updates what are the weight parameters, and the weight updates will help the model to learn the new skill by mapping. If this is the input, this should be the output. So the weight updates helps learn the model on what is the expected input and output cycles are. So this is how the SFT or the supervised fine tuning works, and the training cycle follows this methodology. to learn from the response pairs and not from the rules. So we are not defining any rules that the model has to follow, any conditional logic that the model has to follow. All that we give is input output response pairs and how it learns by using the next token prediction algorithm, computing the loss, and updating the model weight parameters in the direction of reducing the loss. Now, okay, so we spoke about how the fine tuning updates the entire model to adapt to a specific domain task. But when we are adapting the model to a specific task, how the full fine tuning looks like in terms of model architecture. So, a full fine tuning basically changes everything in every layer of the model. So, it starts with the language model head. So, the language model head is changed, the transformers are undergoing a change, the feed forward network is undergoing a change, the embeddings are changed. So, there's basically a change in the entire model architecture when a full fine tuning is being adapted. Now, when you have like a model that is basically comprised of 7 billion plus parameters, and if you make it fully trainable with fine tuning, this is the expected, illustration value that I've given here for the memory, because the memory has to hold every instance of weights, every instance of gradients, and every instance of whatever optimizer updates, and every instance of the activations. So the memory requirement is very insane in this scenario because it has to occupy or account for every updates as checkpoints. So the memory at scale is very massive and it demands a lot of resource in case if we go with the full fine tuning. Now let's see if there is a reason, provided we took a look at how massive it is and how large the memory is required and computation power is required, is it really necessary for us to retrain every parameter? Is there no alternative for us to do some adaptive strategies? And yes, that's how we have the LoRa. So LoRa is nothing but the low rank adaptation strategy. So in case of full fine tuning, you're basically training the entire model parameters. But in case of LoRa, what we all do is we freeze the base model head. So the head is frozen. We're just choosing a selective parameters of a model to be an adapter. So we're just choosing a selective parameters, introduce the trainable matrix only on those selected parameters, and we are freezing the base model. So in case of a full supervised fine tuning, you expect all the 7 billion parameters to undergo the change. But in case of LoRa, which is the low rank adaptation, you'll just expect a portion of it, which is, approximately like 4 million out of 7 billion parameters, which is significantly lower and easier to train. So basically, LoRa just learns the change. It adapts to what the use case is, but not the entire model. So there's only selectable parameters that has to learn, and it's still capable of performing or suiting to a task specific model. Now let's take a look at how the LoRa works. So to see how the adaptation process looks like, let's consider the foundation model in the matrix of D cross D, and this is the weights. So this foundation model head is basically frozen in case of LoRa. And all it does is it just adds two smaller matrices, which is B cross A. And in case if you had chosen for a full fine training, full loop of training, it has to undergo the change with D cross D parameters. But in case of LoRa, all it does is undergoing the change just with B cross A, which is nothing but 2 times D cross R. And here R is nothing but the rank of the matrix, which is much, much smaller than D. So 2 times D cross R is all that LoRa does with the update. But in case of full fine tuning, you'll have to do the square of the matrix, which is D cross D. Now, the LoRa is being represented as the base model plus just the delta of the change, where the delta is nothing but the B cross A. And the rank is typically chosen anywhere between 4 to 16 based on the model configuration that we would like to have. So this is how the LoRa is super helpful and keeping the model adaptation process very computational friendly and achieving the same result How do we attach these adapters in lines, in very few lines of code, right? Because this is really catching everyone's eye, because it's super easy to handle with the libraries. So there is the Hugging Face library called as the PFT, which is the parameter efficient fine tuning. And this helps us to import the LoRa config. And for this LoRa, as we noticed, rank is the major criteria. So this is the configuration parameters that we set for LoRa. So rank is a major criteria where we set it to 8. And there is an alpha. So alpha is nothing but to what scale the parameter has to update. So that is something that we can set it and fine tune according to our use case, which is 16. And we are targeting what are the specific selected parameters that we want to update, right? Since we chose that it's just selected parameters, what are the parameters? So in this case, we are choosing the query and the value pairs. And this can also be changed to whatever use case we want. And our task type is just a casual learning model. So this is the wrapper function, get PFT model. We are putting in the base model, we are putting in the config. So this is a config that holds all of this parameters for LoRa. And now we're just printing the trainable parameters. So the base model is untouched with the heads being frozen, and the adapters are just choosing a smaller A cross B matrix. In this case, it is query value, and the trainable parameter is like very insignificant, less than 0.08% of the entire parameters. So yeah. And how do we measure? How do we measure if the adaptation really worked, if LoRa really helped our model to adapt to our specific domain task? So we identify that based on the 4 dimensions. One is the base accuracy. So we are doing if it really matches with the base model. And then we are doing the LoRa accuracy, where we are identifying the LoRa exact match. And we should also identify what are the trainable parameters that LoRa has chosen and what is the adapter size. So these are the 4 dimensions on which the LoRa is being evaluated. So here's an input, for example, artificial intelligence improves efficiency. Now, base model, what it does, it says, sure, here's the corrected. So our intention was to correct the misspelled sentence, right? We see here it's intelligent spelling is wrong and efficiency is misspelled. So base model, it gives us output something like, sure, here's the corrected sentence, and it gives us this. So these are the unwanted sentence, right? Because base model does not know what is the intended or specialized task. It just knows everything, right? So it just gives all the unwanted sentence. But now the LoRa adapted model just gives us the corrected sentence. The reason being, LoRa adapted model is just adapted to be a spelling corrector, and it knows it's not designed for any other task. So it knows what its intended task is. So it just performs the task, specialized task. So this is how the adaptation helps scale the model to a specified use case with a very smaller computational power and model parameters. Now, here's like an overall example on what a full fine tuning is and how LoRa outperforms it. So parameters updated is everything, while in LoRa it's a smaller subset. GPUs is higher and this is on lower end, while the storage is like it has to maintain a full checkpoint, while this is just a smaller adapter, which is B cross A. Now flexibility, it is very strong. This is highly modular, which means it is just designed for a specific task. Deployment, it's like a separate model, while LoRa is, again, the base model is still intact, and adapter is the one that's trainable. So it's just a combination of base and adapter. Now, with this, I have an illustration on the LoRa. So how do we teach an LLM a new skill with SFT and LoRa? So this is our task here. Now we are loading. So first thing is we are loading the Hugging Face model, which is the base model. So this is the base model, which is an LLM with 135 million parameters. So this base model has 135 million parameters, and it is a base model that is basically an instruction-based learning model, right? So we are considering this model, and we are using this for an SFT, which is the supervised fine-tuning task, and we are performing the LoRa updates on this. Now the model is loaded, this is the base model. Now we are creating a data set. So our intention of this model is, let's say we have a word, so this model has to append the suffix ish and complete the word. So if this is the example, if this is the input hello, here's the input hello, so my model has to append hello with hyphen and ish, learn with learn and hyphen ish. So this is just a simple illustration that I want you all to see how we can train a model using the SFT by just involving a base model that is capable of doing everything. Now let's see how the base model looks like, right? So I'm just passing this as the input list of demo words that I want. Let's see how the base model is capable of to do this task. Now I am giving the prompt. So, this is a prompt. Add ish to the end of the word. Example, this is a few short prompting. So if this is input, I want this as the output. If this is input, I want this as the output. So I'm just giving the prompt and I'm giving it with the data set. Let's see how the base model performs without any change to base model. Now, this is the predicted output. This is the actual output. This is correct, while there are many correct. So this is the result. 7 out of 13 are correct with respect to base model. Now, that's okay, but we want the model to do better because our intention of the model is to have it corrected, have it exhibit this behavior, right? So how do we do it adapted? Now, consider the LoRa, which is the low rank adaptation model. Now we are defining the LoRa config values that we saw, which is the rank, alpha, dropout, and the task type is casual learning model. And we're wrapping it with the wrapper that's available from the Hugging Face. This is an inbuilt wrapper, and we are passing the base model plus the LoRa config that we defined here. Now, the trainable parameters in this case we see is 3 million out of 138 million. In case if you had chosen a full fine-tuning, a fully supervised fine-tuning, you will have to update all the 138 million. But in case of LoRa, it has helped us just update 3 million and not the 138 of it. Now, which is hardly 2.67%. So let's create the training loop for it. So with training loop, we will have to define what is the output directory, what are the training epochs, and I'm just intentionally setting it to a very lower epoch. In real-time scenarios, the training epochs ranges from hundreds to thousands, right? And for this illustration, I'm just setting up very lower training epoch. And similarly, even the accuracy is not as great because our epochs are very small, right? If you want the accuracy to be good, the model has to undergo a fully trained cycle with hundreds to thousands of epochs. So that's the caveat here for demonstration. Now we are invoking the SFT, which is supervised fine-tuning trainer, and we are now evaluating the fine-tuned model. Now we just fine-tuned the model using the LoRa. Let's see how it works. Now here, after evaluation with just 20 epochs, 20 epochs is, I would say, very insignificant because I want to show it very quickly for this demo. And we see 9 out of 13 is being correct after doing the LoRa updates. Now, before the model learned, it was 7. Just with 20 steps of learning, right? Just with 20 steps of learning, it was able to improve and give us 9 out of 13 values as correct. So this is how, but then if you want to have like a full accuracy, you will have to train it for, I would say, anywhere between 500 to 1000 epochs and let the model undergo a full round of training. And we are definitely going to see about 90% of accuracy, anywhere close between 97 to 99% of accuracy for this model. So this is how LoRa helps with the fine-tuning of foundation model. Now we're left with just one concept, which is the reinforcement-based learning. Now we just took a look at what SFT is and how LoRa empowers it. So with SFT, which is supervised fine-tuning, we are supposed to provide a labeled data set and it gives us the correct output. Now, let's say we're just providing one output for one input. What if we have multiple outputs ranked with preference, and if that's passed to a reward model and allow the reward model to choose what preference of answers it requires? So that's called as the reinforcement based fine tuning on human feedback. So once we have this reward model trained, there are optimization techniques like PPO, GRPO, which is like group relative policy optimizations that helps strengthen the reward and give the correct probability of precedence. So now, the response in this case is like, response A is preferred, which is correct, concise, while response B is correct but verbose, because this is the preference pair it results in. So it gives us multiple preferences, but one will be with higher rank. The second one is closely related, but not the preferred response. So that's the difference between like SFT and the based, reinforcement learning from human feedback. This is the overall block diagram, how it looks like. So we're going to generate multiple responses rather than a single response. We're going to generate multiple input output pairs with input mapped to multiple output responses. And there is a human annotator to annotate or label or rank these answers based on the precedence. So they're going to rank, and then we are training the reward model based on this output that's basically annotated by the humans. So the reward model understands, in case of this input, what is the preference the human looks for. So it understands the precedence by seeing the ranking of the response. And then once we have the trained reward model, we are going to optimize the policy using the PPO, which is PPO or GRPO. These are the optimization strategies. So we are going to optimize these by strengthening their rankings and giving better probability results. So this is how the cycle looks like, and this is like a very good advanced learning fine tuning strategy for a model, because because in today's world we might not know what are the human preferences, right? So one might prefer very verbose while the other might prefer very concise answers. So this model helps us give multiple outputs with precedence, understanding what is the human preference. But this also has one caveat, because in case if the reward model goes with an adversarial answer where the intention of the human is to train a very bad model, that's called as reward hacking, then the reward model also learns just the answers that the hacker wanted to train the model with, where the intention is not to have like a good reward model. So that's one caveat that exists with the reward model, because it basically understands whatever human annotates, right, with the precedence. So with this, let's see how the policy optimization helps strengthen the model by reinforcing or suppressing it. So it calculates the advantage of it. So the advantage parameter is nothing but you know, it subtracts the rank with the mean of it and divides by the standard deviation. So anything that falls greater than this value is basically strengthened or it is reinforced. Anything that follows below this advantage value is basically suppressed. So this is how the group relative policy optimization basically strengthens or suppresses the probability values in a way that makes the probability look good based on the human preference or precedence. So with this, let me quickly show the final notebook for this, where we are doing the same LLM, teach the spelling, but using the group relative policy optimization. Let me go all the way. So in this case, also we're using the same Hugging Face model, but now in this, the task is not just to add the word ISH. In this, I'm giving a task to spell it individually. So let's say if it is word, I wanted to spell it out with hyphens and separating each character. If it's a word, it's word. If it's triumph, it is triumph. Now, how do we use this for SFT and the RLHF? Now with SFT, all we're going to do is, first thing is we are going to identify its uh, base model accuracy. Well, the base model produced 0 words correct. Now we are enhancing by using the LoRA and using the SFT. And with this, we are doing just on a smaller scale. The learning steps is just 20. I mean, the epochs is 10. So this is a very smaller training cycle. But yeah, it predicted 13 out of 20 words correct, right? And here even though you see everything wrong, which means it is calculated per word basis. So in this case, it is getting better because the training cycle was really low, just 10 cycles. Even with 10 cycles, it was able to improve and ramp up the model. Now let's go with the GRPO flow, because the previous one covered the SFT flow. With GRPO, we are establishing a rank model. Let's say if the character is correct, reward it, which means we are updating or incrementing the score by increasing with 1. Now, in case if the character is not matching, penalty. So you will have to reduce the score by 1. This is how we are, training the reward model by assigning the reward score to it. Now, with the reward score, and also we saw that it is not just one answer, it completes with multiple answers. So it basically generates 3 to 4 responses for each word. So that's how the reward or ranking model works. And it's calculating the mean and the standard deviation based on the reward scores. So finally, you train the reward model using the data set, and we're using the GRPO trainer, passing the reward function. So here's how we are calculating the mean and the standard value and giving the example, right? So here's how the training has been performed. So it does the full round of training. And also in this case, for each word, there is like 4 corresponding words generated. So here's how the full word round of training is performed. And finally, you evaluate the model. So in this smaller set, it was able to predict 2.64 out of 7 words. Now again, here, the training cycle was also very minimal. So it was able to find 13.97 out of 20 words correct, and this is on the test data set. So when you involve a higher training cycle, you'll see a significant increase in the output. But this is how the GRPO, SFT, LoRA, and the reinforcement learning works and helps with the model adaptation strategies. And yeah, so we have wrapped up all the adaptation strategies, what foundation model is, what LLMs are, and how we fine tune to a specific task scenarios. So I just want to wrap up this with one keynote here on how to choose the right models. So let's say you have a current or external knowledge base article, go with RAG, which is the retrieval augmented generation model. And this requires a complete different session for us to deal with what RAG is, what are the different RAG advanced techniques, how RAG operates with embeddings and retrieval strategies. And that's how RAG empowers using the external knowledge base articles. And in case if you have need more reliable task behavior where you want it for a domain specific task, go with the fine tuning strategies, either a supervised full training or LoRA, which is the low rank adaptation. So the supervised fine tuning is basically a full training, and while LoRA is just on a adaptive basis. If you have a limited GPU or many task variants, LoRA is ultimately the one, because with limited GPU, you cannot attain a full training on a supervised fine tuning. And if you want a preference, right, or style alignment rather than just one answer, go with the reinforcement learning human feedback. And if you want a general purpose model, go with the foundation model that starts with pre-training approach, where you're passing all the diverse broad corpus data. So this is how we make a choice to choose the right ideal model for our use case based on the constraints, based on the availability, based on our purpose of training, what the objective is, and what our style, tone, alignment, everything looks like. So this is how the decision is primarily made in any of the enterprise production systems or any of the architecture determination systems. So just to sum it up, this is what we learned about applications of Gen AI, what are the foundation model, what are the evaluations, the neural networks, how do we generate text using the next token prediction algorithm, what is LoRA, what is parameter efficient fine tuning with SFT, what is reinforcement learning, what is GRPO, the optimization strategies. And this is how each one looks like in their own space with your own capabilities. And yeah, we are almost towards the end of the slide. And yeah, thank you so much for attending this and listening in. While I have attached few of the resources that's been more helpful for learning. So this is a QR code where it links to the document and provides with all the resources that help me learn the strategies, the adaptive models, the foundation models, and everything. So I just wanted to share with you all. That might be helpful in your learning as well. So yeah, thank you all